board. This is 2.4, the second derivative. What the first derivative, what we've been finding, and I've been saying the slope. Well, that's what you're finding is, that's the formula for the slope. It's just weird looking. When you find the derivative of the derivative, what you're adding is the second derivative, and it's acceleration. So the first derivative is velocity, and then the second derivative is acceleration. We're going to talk about the notation and then how this is good to find if something's concave up, concave down. All right, so if we have a roller coaster and this is our function, and a lot of times you hear this called a position. Okay, that's not bad to say that. Your function's the position of something. Your first derivative's the speed. Your second derivative's the acceleration. All right, so if I have a particular time and I put into some function, pretend there's a function there, it will give me what the height is. If I find the derivative of this function, which is what you're doing right here, you're finding the derivative of the function, I can also see at a particular time what the velocity of the roller coaster was at that particular time. If I find the second derivative, notice there's two little prime things now. The second derivative is what it sounds like. You're just taking the derivative of the first derivative. So you're doing the derivative twice. This is why we've got to get the shortcuts, because most of you hate doing this once. Well, how'd you like to go do it again? So we're going to get to a point where we say, well, find the first derivative. You'll be able to look at it and find it, and then take the derivative of that. Okay? And so, in other words, the second derivative, which is acceleration, is the derivative of the velocity function, or it's the derivative twice of your position function. And remember that in the beginning of this course, we answered this, and we came up with, a number. And we said that number is the slope. I'm guessing you guys, I'm sorry if you guys can't see that over there, but we had our function, we came up with a slope. Then we said, get chalk all over me. Then we said, well, what if you don't know that value? Okay, meaning that in a perfect world, we want that value to be what? Perfect. So we're saying if we let this go to 0, if you remember, we ended up with an actual function here, and in this case, we ended up with a 1 over x. So because when you take a derivative, you get a function, you can take the derivative of that function and you get another function, and that's what the second derivative is. So you get another function that now you can plug in whatever you're plugging in to get it. So the acceleration, a of t of the roller coaster, is given by taking, again, the derivative of the. All right, so this is our function. This is, remember, a couple of classes when we first introduced derivatives. These are all the different ways. Well, guess what? There's that many ways to write the second derivative. I probably use and maybe this more than any of them. Okay, and I will say, I know this stuff for many of you guys. I'm sure some of you get sick of hearing me saying, those of you that were in high school, I didn't freaking take this in high school. So if this is new to you, I will tell you, find the second derivative. Or if I say find acceleration, I don't have a problem. Students come up to me all the time during the test. Do you mean find the second derivative? Do you mean to use this formula? Ask me that stuff during the test, because I don't want you doing something and you're going off on the wrong trail and you've spent 30 minutes and now guess what, time's up. Okay, but I will try to, limit myself to, whichever one of these. I don't like this because I don't even know, what's my variable of interest. And this is okay, but this is my two-step thing that I'm taking the derivative. Okay, so what the second derivative also gives you, we said it's acceleration, is it tells you the concavity of your curve. It tells you if it's concave up or concave down. So notice here is 1 prime, and that's 2 prime. 1 prime is my first derivative, which is my slope. My slope's less than 0. That's obvious, right? My slope is negative. Slope goes to 0, and then my slope goes positive. So in other words, this slope increases from negative to positive. So you're slowing down, you stop, and then you take off. And what happens here is you get your second derivative ends up being concave up, you have the concave down, but you start out first derivative positive, go to 0, second derivative negative. I'm saying, even though you don't see it in the definition, I'm saying goes to 0 for a reason. That's one way you can figure out if something's concave up or concave down. You can find your 0 point where your derivative equals 0, pick a value to the left, pick a value to the right, and see. If you get a positive and then a negative, then you know it's concave down. All right, so in a graph of any function, we can actually look at these tangent lines, and that's what we're doing, okay? When we keep saying we're finding derivatives, we're interested at that point right there. If I drew a tangent line where I only touch that point right there, what's the slope of that line? Then I'm moving, basically going down this line to see if it's concave down. Now, it's funny how you guys remember things, and this is something I never thought of. My students last semester said, you're positive, you got a smiley face. You're negative, you got a negative face. Hey, makes sense, right? So it's an easy way to remember your second derivative. If you take the second derivative and you get a positive number, meaning you did all this stuff again, then that says at that value, whatever number you plugged in, it's going concave up. If it's negative, you get concave down. At 0, if our second derivative is 0, then there's no concavity. All right, so what we're going to do is we're going to look at each one of these. So this very first one, f of 2, is that positive or negative? I hear negative. In other words, I'm looking, this is just the value of the function. Again, this is pre-calculus, before you got in this class. You already knew how to do that. This is just what's the value of the function. What's f prime of 2? Negative. And that's what we just said. If the second derivative is positive, or we can say this different, if I have a graph and I see that this is concave up, then I know my second derivative is positive. All right, first and second derivative everywhere is positive. So my first derivative everywhere is positive tells me I would have a graph that's going up, right? My first derivative is my slope, it's increasing. My second derivative everywhere, so the graph would look like this. Makes sense, my first derivative is positive. It's increasing. My second derivative is positive, that's why I'm getting my concave up. And these are like your homework questions. And I see a couple of you guys writing. As I remembered, I didn't put these in your slides, these pictures. So you need to draw the pictures. I left the slides blank to, I don't know why, I just did. All right, so again, first derivative positive, second derivative positive, concave up. If I look at the second derivative everywhere is negative and the first derivative positive, it's still increasing, but it's going concave down. Okay, so this section, and you might argue and say, well, but eventually it looks like it's going to start to turn, but we're just saying this section right here, this would be an example where the first derivative is positive, it's increasing, and the second derivative is negative because it's going concave down. Second derivative everywhere is positive, first derivative negative. So in this case, my second derivative is positive. That's my smiley face, concave up. But my first derivative, my slope. And again, if this is new to you, start writing this. Every time you see first derivative, slope. Second derivative, at this point, all we've really, we said it's acceleration, but that tells you your concavity. Concave up, concave down. Okay, until you kind of get, because it takes a while. I've noticed students that are first in here, I say, well, what's the first derivative? And it takes a second to think, oh, it's just the slope. Okay, so we're just, first and second derivatives, negative means certainly this function's going down. Okay, my first derivative's my slope's decreasing. And then my second derivative's negative, so I'm getting my concave down. So again, this is exact questions that you'll have in your. All right, this is a homework question. The table gives the number of passenger cars, C equals this function for time, in millions in the U.S. in the year T. Now, a lot of times when you're given tables, and sometimes I'll do it just to mess with you, don't think this top is always your X and that's always your Y. Okay, this is pretty easy to see that that's my y because it says c equals my function, which is my y. A good thing to pretty much always in this class is time that's moving will always be on your x-axis because this depends on time. And remember we say your y variable is your dependent variable. But again, that would be something I would come ask during the test. Do you mean this to be my x and this to be my y? All right. Does, I don't know. The first derivative and the second derivative appear to be positive or negative from 1940 to 1980. What do you think?
Let's see, the first derivative would be positive.
It's increasing, makes sense to me.
The second derivative is negative because it's going concave down.
It's going concave down.
See how it's slowing down though?
Ooh, check it out.
Because 133.7, 133.6.
Okay, but can't your slopes get steep and start to slow down? And then maybe what's going to happen if if it's slowing down, you're not accelerating as fast, but you're still accelerating. You're still going faster. In other words, your speed's still going up, but as you're saying, this distance here, you're starting to slow down, right? But you're still
Thinking that it's going to fall, just use the graph.
exactly, yeah. Because like as you're saying, when you hit here, if I had more information, maybe it is going to start to go flat. Mm-hmm. Now it's like, what's with the red? Be sure, I'm not sure you'll need something to graph with Tuesday on your test, but just in case, have something. Definitely have a calculator, okay, for your test. If the video's screwed up. All right, here's another one. In a study of deaths in the U.S., it was found that the deaths from aerial transmitted diseases as a fraction of all the deaths could be very well described, shown by this graph. I know we just take for granted there's graphs, but hopefully you get where you can read these and notice that we have years. Okay, so we're just talking about, the study of deaths for particular years and then the fractional values. Determine whether the function is where the function is concave up, where it's concave down, and what in real world. This is more like what I ask on a test. If I say what does the concavity mean and you answer the second derivative is 0, I probably will write SA on your test. Smart. UTSA, there we go. All right, so where's the function concave up? About, at my x values. About 40, looks like it's changing. And then where's it concave down? Up here. So you can see the actual graph. So this is going to be those of my hotshot kids here where it changes from concave down to concave up. You remember what that's called? All right, so that's your inflection point you'll learn about later. Meaning that's where it's changing from concave down to concave up. And so the fractions of the death is decreasing and here's for you, Raphael, you were talking about it. In this case, we could say our acceleration is still decreasing, but this slope is getting less and less and less and less. Okay, but it is still actually changing. And then the very last part is just kind of a review of remembering the difference between, I don't know, it's a word place, they put it in this book, average acceleration versus instantaneous, which if you notice here and here that's average rate of change, that's instantaneous. Yes?
So for the acceleration of the second